Anton is a PhD candidate in the chair for digital fabrication technologies at the ETH in Zurich. And she's also associated to the National Center for Competence in Research Digital Fabrication, the NCCR Digital Fabrication, where she leads the interdisciplinary research in concrete 3D printing. Anna received her architectural degree at the TU Delft in 2014, and she continued her research until 2016 at the Hyperbody Research Group in Delft. And while her scientific research addresses complexity and emergence in architecture, her designs exploit materiality encoded for digital fabrication. Her current doctoral thesis, Tectonics of Concrete Printed Architecture, investigates robotic concrete extrusion processes for large-scale prefabricated building components. Thank you for coming to Frankfurt.
Thank you. Thank you for having me here and for the kind introduction. Today I will talk to you about 3D printed columns, which is a chapter of my doctoral research into tectonic principles for concrete printed architecture. We know that since the invention of Portland cement in the 19th century, and with continuous innovation in material formulation, processing, and the structural applications, concrete has become, without any doubt, the most used material, construction material in the world. So much so that it has shaped a uniform image of our cities, creating serialized building components that most of the times use more concrete than it is actually required. I have selected some examples of digital fabrication methods employed in the realization of formworks. We know, of course, about hot wire cut or milled foam. We have robotically held in place fabrics, knitted, stained place, thin formworks, and even 3D printed formworks. All these projects show that digitization and customization can optimize material use and can help reinvent concrete aesthetic for a new interpretation in contemporary design. The moldless shaping of concrete is led by Professor Robert Flatt at ETH Zurich as one of the research streams into the National Center of Competence in Research Digital Fabrication. This research stream is funded through the Swiss National Science Foundation, and it includes projects like mesh mold, eggshell, and concrete 3D printed, which aim to eliminate the need for traditional formwork in concrete. It is also based on the ecological advantage of no-waste construction and shape customization of digitization. So, moldless shaping of concrete shifts the focus of concrete research from formwork manufacturing to controlling the properties of fresh paste in its transition to cured concrete. In this context, 3D printing with concrete emerges as a new technology, offering unrivaled material optimization possibilities and novel customization, because no formwork is required and concrete can be placed in space following very intricate geometries with hollow features and optimized shapes. At this point, I would like to quote Julian Vincent, who more than 30 years ago stated that in nature, shape is cheap and material expensive. Until recently, the opposite was true for concrete industry, in that complex shapes were very difficult to construct, while materials were seen as an infinite resource. I will come back to the importance of this observation throughout my presentation. Now back to concrete printing. There are essentially four main processing requirements for 3D printing with concrete. One is that the material has to be fluid enough so that it can be pumped to the point of placing. The material should hold its shape after being forced out of the nozzle. Then a particular layer of concrete has to hold the weight of the additional layers that come on top. And of course, the process should be stable and repeatable in the same testing conditions. If we look at the case of a column, we see that the print path is usually very short compared to the vertical height of it, and this translates into very strict material properties. At the bottom here, concrete should be almost hardened while we still print at the top. From a structural point of view, the column geometries have a very high risk of buckling during fabrication because of the horizontal cross-sectional area to height ratio. There are several examples of vertical elements which were produced digitally without the use of a traditional formwork. Of course, we have smart dynamic casting from ETH, where a numerically controlled formwork moves vertically to replicate the traditional slip forming technique. And we have chemically activated mortar that continuously fill this moving formwork to create section changing elements vertically. Then the amalgama column from the Bartlett School of Architecture was produced using a hybrid technique of extrusion of concrete and used salt as an additional material support. It is a combination of layered extrusion with particle bed 3D printing. This is why we have these very generous overhangs. Then we know the 3D printed formwork from X3E, which is the successful implementation of 3D printing into a real structural building element. Sections of this formwork were assembled vertically, and ultra-high performance concrete was cast to create this very complex structural element. Finally, we have the liquid rock installation, which shows great advancement in the processing strategy, but also in the geometric freedom of the print path. The installation was fabricated using the Bauminator technology from Baumit. So 3 of the 4 given examples use a set-on-demand concrete strategy. So set-on-demand, or hydration control of cementitious materials, was introduced for concrete 3D printing in 2016 by Gosselin and the co-authors. And it requires a specially developed tool that is able to intermix the mortar with activators to trigger the cement hydration. So if we look closer to the structural requirements that an element has to fulfill during printing, we see that we need a linear increase for the first few layers, and then a very sudden strength increase to overcome buckling. This is according to Reiter et al. This brings me to the point of introducing the 3D printing process developed at ETH. Even if the print fails, there is something fascinating about how the material behaves. Basically, we use one industrial robot, which is mounted on a 3-axis gantry system, our famous RFL. We have a big batch of concrete that is heavily retarded. The mix should be sufficient enough that it lasts for the whole print. And this mortar is pumped into a continuous cavity pump that delivers the material to the printing nozzle. Another pump delivers the additives into this active mixing tool. Material is deposited on the print path, while the robot is controlled online So streaming the data online proved to be very beneficial in the upscaling process because we are able to stream as much data as we need. This was possible by using the open source software developed in the NCCR framework, the Compass and the Compass Fab specifically. What it is perhaps different to our printing process is that we use a very soft and ductile filament that is able to have a very fast strength increase. See here, the red curve. This very soft filament ensures good layer bonding and more flexibility in choosing the printing parameters. Because we print a soft material, the extruder geometry doesn't entirely shape the concrete filament as it leaves the extruder tool. The filament size can be calculated as a continuous variation of flow rate and printing speed. At this point, we can start translating the material system into geometric affordances for fabrication. Thus, we look at types of print path, like what are the aesthetic implications of self-avoiding print path or self-intersecting print path. Then we can optimize one layer for fast printing speeds. In this case, you can observe how we avoid sharp turns by using the possibility of self-intersecting print paths that the material allows for. To determine the design space, we also look at the overhang capacity of our printing system, which is in the range of plus minus 25 degrees for geometries with small areas of overhang. Layer height variation is another design parameter. It can create 3D interfaces between components. But perhaps the most promising characteristic of 3D printing with concrete is having internal geometry. It offers stability during printing by creating these vertical cores that support the exterior overhangs. But it also creates hollow concrete elements, which are lighter and make better use of the material. The compressive strength of our material is already in the range of structural concrete and has no strength variation correlated to the layer orientation. It has around 70 megapascals, and it can be used in pre-stressed systems. But besides the aesthetic, the printing quality is determined also by the mechanical behavior of the printed parts. In 3D printing, there is a high risk of weak layer bonding, as well as an increased possibility of defects that appear during printing. In general, because we print very fast, we have now not enough time to create cold joints in between the layers. However, if we have defects like these small air gaps, they behave like cold joints. So we can definitely expect anisotropies when we 3D print with concrete. Not everything can be printed, but we try to map out all the geometric affordances that the system can allow for. We can decide on the layer size, on the filament, on the printing filament. The fast strength buildup allows for very fast printing. However, not all the machines can drive at that speed. So we have to provide a very smooth print path for fast speed. We know that internal geometry gives additional support during printing, as well as self-intersecting print path. And we also know the maximum overhang capacity of our system. Knowing all these design aspects, we chose geometric generative engines that make sense to use to be used in such a context. So we opted for trigonometric functions and mesh subdivision. For this, we develop an app that transforms a generic computational mesh of a given height and diameter into a 3D printable column. The first case of the trigonometric functions, we start by controlling the trigonometric functions with 3 parameters: frequency, amplitude, and phase. which are later used to displace the vertices of a high-resolution mesh given as an input. In the case of mesh subdivision, simple rules are applied iteratively to create an ever more complex mesh. We start with a low-resolution polygonal reference, and through subsequent subdivisions, we create a high-resolution mesh. The analytical information embedded in the app offers information about the group type, face area, face perimeter, which are used to assign subdivision rules. And also we have information about the vertical angle of the mesh face, which ensures safe overhangs for printing. This is how the tool looks like. In the center we have the design. We have an indication about the cross-section. Control of the mesh here, and these are the design features. The modular app architecture was developed in Python processing and generates a mesh object, which is later on imported in Rhino and Grasshopper for computing the fabrication. The Python modules are also compatible with Grasshopper. The trigonometric functions allow for designing with the print path itself, and the core can be added as a distinct geometry, which can be optimized for fast printing speeds. The variable layer heights allow for the creation of non-planar 3D interlocking seams, and the smoothness of the print path was essential to ensure that the robot reaches the target speed, which continuously varies between 300 and 450 millimeters per second. In the case of mesh subdivision, the design space is extended to geometric features like porosities that are created through overhangs that meet in mid-air. The subdivided mesh generates its own internal core. But in order to print the intricate design, we had to significantly reduce the printing speed to almost half of what was possible with the case of the sine functions. So the development of this software marked the starting point of concrete choreography, a 10-week project, part of the Master of Advanced Studies in Architecture and Digital Fabrication from ETH Zurich. Students were introduced to this tool, which they explored and furthered, and then used to design and fabricate the 9 2.7-meter tall columns that were part of the second stage of the Origin Festival of Culture in the Swiss Alps. We started with a concrete base on which we printed the column. Here you see the process operating at its real speed. The final products were handled as prefabricated elements and were moved on site one day after casting the concrete core and reinforcing the columns. And again, they were positioned on site with a crane. Here you have the final stage installation in the beautiful alpine setting of the Swiss Alps. Okay, so this one runs. You see how the students designed the app. And another snapshot of the fabrication process. The columns are printed with a hollow core that is later on reinforced with a regular mesh, and the core is cast to create this structural bond between the concrete base and the column itself. What is very important to mention is that the research environment of ETH is a proof of the need for interdisciplinary collaboration in the field of digital fabrication. And also, as a step to nurture this collaborative mindset, we share with our students all the research information that we have. And this was shown in the fast realization of concrete choreography, which took from design to full fabrication only 10 weeks. Another column was designed using the mesh subdivision engine. This tested the limits of our fabrication process because it was printed as a full height of 3.1 meters, printed in a continuous process of 1 hour and 50 minutes. This column was post-tensioned using 4 post-tensioning cables that run through the hollow, intricate core. And the total print path of the column is of 1 kilometer, which was printed at a filament size of 25 millimeters width and the 5 millimeters layer height. This is the evolution line of the column typology embedded in my research. The design methods were developed simultaneously to all the other fabrication parameters. And in this way, we somehow proved the necessity for developing new design algorithms and the new design thinking for the methods that we develop. When we put all this data together for the case study of the column, we see a large variety of sectional profiles that have hollow internal structures. They provide many opportunities for reinforcement, other casting some parts of the printed element or post-tensioning. We have a large array of possible surface textures. We can vary the printing parameters depending on the design complexity. But what this experimental work shows is that concrete elements can be redesigned and optimized to use less material. So with this research, we have shown that we are able to fabricate concrete 3D printed column. For the case of this particular element, we were able to print a 3-meter tall element in less than 2 hours. This process can be further extended to other building components, like beams and slabs, thus taking us closer to a vision in which concrete 3D printed elements can be used directly in buildings. Also, this novel materialization of concrete aims to contribute to a body of work aligned with Julian Vincent's description of material efficiency inside natural form. By exploring the potential of complex geometries, I encourage the use of novel technologies to aid in the understanding and creation of harmonious structures that have the same level of sophistication and lean material use as those encountered in nature. I would like to thank all my colleagues for this fruitful collaboration, and especially to Professor Benjamin Dillenburger for his support, but also to Timothy Wengler and Lex Reiter for sharing their expertise in material design, material formulation, and process development. And thank you for your attention.
Thank you very much. It needs quite a few people to make something like this happen. Are there questions?
Thank you for this talk, for this presentation. It was really nice. On one of your last slides, you have shown the parameters for the different geometries we have realized. I could see that for even the same layer height, you had quite significant differences in the printing speed. What was the reason?
The reason was the step of controlling the concrete pump in a digital way, so controlling the flow rate of the pump in a digital way. That was a definitive improvement of the printing process.
But you used always the same material composition, and you had just to adjust the flow rate to the geometry you want to realize.
Yes, yes.
Even for the same layer height. Okay.
Yes.
Thanks.
Hi, Alban Mallet from X3. Thanks a lot for the presentation. I have two different questions. The first about bonding between layers, that you say that the material is completely the same in both directions. did you have to develop a new way of making test loads on those prototype, or you just use like classic 4/16 for flexural and compression, or did you develop new kind of tests? And
so the tests I showed there with the prisms, they were cut out samples of larger 3D printed elements.
so you have been because I saw that you have really small layers, so you are not printing like a 4 centimeter beam.
No.
So you managed to remove the little bubble from your calculation to be sure that you don't have like difference in the way you're breaking your elements.
So the elements were measured on their exterior geometry without taking out the defects. So in the case of the prisms with defects, then I considered the material as homogeneous. I didn't take out any error.
Okay, thank you. And I have another question about the post-tensioning you have made. Do you have some result to share about the resistance you managed to add with the post-tension in flexural and compression strands?
Not yet. We are working on publishing the results.
Okay, thank you.
Okay. What I really enjoyed was to see that you do not only fabricate those columns, but you also develop a design tool that allows others, in this case the students, to design these columns. And I think it's exactly this process that needs to be developed from the first ideation to the actual materialization. So thank you very much again for your talk, and we will have a 15-minute coffee break until we have the last 3 lectures.